In this video and the next video, we are going to look at solving non-homogeneous second-order differential equations. In this video, we are going to look at the method of undetermined coefficients. And this method is a fairly straightforward method, so that's its main advantage. Its main disadvantage is it's limited. In particular, it's limited to where g of t, our function on the right, is either a polynomial of degree n, an exponential function, or a sine or cosine function. And this overview slide looks very dense, but that's because I have two theorems which take a lot of space. And also the method of undetermined coefficients seems to have a lot of steps, but it's really only three. It's just that step 2 gets broken down into cases of where g of t is the polynomial, the exponential, or the sine. So actually it looks very dense, but it's not as bad as it looks. We will start by looking at this theorem, which relates solutions of non-homogeneous differential equations to the related homogeneous differential equations. In particular, this theorem applies to looking at this form here, second order linear, you can see it's linear, non-homogeneous differential equations, and we relate that to solutions of the second order linear homogeneous differential equation. And just to note, you'll also see that the coefficients for this theorem, the coefficients do not need to be constants. They can be functions of t. And this theorem says if we have two solutions, y1 and y2 of the non-homogeneous linear differential equation in this form, then their difference, y1 minus 2, is a solution of the corresponding homogeneous differential equation of this form. In addition, if we have y1 and y2 is a fundamental set of the homogeneous differential equation, then y1 minus y2 is equal to, can be written as a linear combination of your fundamental set of solutions. And the next theorem applies to the non-homogeneous linear differential equation here. So again, we have a second order, you can see that. It's linear, it's non-homogeneous because of this g of t, and the coefficients can be functions of t. So what we have is the solutions of this equation can be written as a linear combination of the solutions of the homogeneous equation, the fundamental set of solutions, plus this capital Y of t, which is a particular solution of the non-homogeneous equation. Then last, we're going to look at using the method of undetermined coefficients to solve equations of this form. This is second order linear, non-homogeneous because we have the g of t with constant coefficients. And one of the main advantages, again, of the method of undetermined coefficients is it's fairly straightforward. The limitation is that it applies when g of t is an exponential function, a sine, a cosine, or a polynomial, or sum or products of these functions, so we are limited. In my overview slides, I usually like to put one example, so I had to do a second slide. So here is the method of undetermined coefficients, and here is an example that we will be solving in our video with this method. We will start with this theorem here, which gives us the relationship between solutions of the homogeneous and the non-homogeneous differential equations. So if y1 and y2 are solutions of the non-homogeneous linear differential equation, which is this form here, the y double prime, giving us, it's a second order, y double prime plus p of t y prime plus q of t y. You can see that it's linear. You can also see because of the p of t, q of t, we do not necessarily have to have constant coefficients, and it's non-homogeneous because of the g of t. So again, we have y1 and y2. They're two solutions of the non-homogeneous linear differential equation. Then their difference, y1 minus y2, is a solution of the corresponding homogeneous differential equation, which is this equation here, this left-hand side equal to 0, or y prime plus pt of y prime plus qt of y equals 0. If, in addition, y1 and y2 are a fundamental set of the homogeneous equation, the one that's equal to 0, then y1 and y2 is a linear combination of the fundamental set of solutions. And we can prove this, and actually it's not a very difficult proof. We start our proof with the premise of y1 and y2 as being solutions of the non-homogeneous differential equation. So we say y1 and y2 satisfy our differential equation, the non-homogeneous, so equals g of t. And what we want to show is that y1, y2 is a solution of the corresponding homogeneous equation. So I've written that down here. We want to show y minus y2 satisfies the homogeneous equation. So when we plug in y1 minus y2 into the homogeneous equation, L of y1 minus y2, we get L of y1 minus y2 because this equation is linear, and I have that proof down here because L of y1 minus L of y2, plugging that in, I get y1 minus y2 double prime plus p of t y1 minus y2 prime plus g of t y1 minus y2. Because the derivative and multiplication are all linear functions, we can then separate this out. The derivative is linear, so we can make this y1 double prime minus y2 double prime. Here, we can put the prime on the y1 and the prime on y2 and then multiply each by p of t. And here, g of t y1 plus g of y2, g2 of y2. I'm sorry, this should be just g of y2. And then we can group our y1 terms together. We can group our y2 terms together. And what you see is that is equal to L of y1 minus L of y2. So this blue part just explains how I got from this line to this line. Or it's something that you can say because the derivative functions and the multiplication and addition functions, which is what L of y is composed of, are linear, you can separate these out. Then my last step is to say my L of y1, well that, because it satisfies the non-homogeneous equation, is g of t, and then I subtract L of y2, which also satisfies the non-homogeneous equation, so that's equal to gt, so we have gt minus g of t, which is equal to 0, and therefore y1 minus y2 satisfies the homogeneous equation. The next theorem we have is about the general solution of the non-homogeneous equation, and the general solution takes this form. It's the fundamental set here, set of solutions here, plus the particular solution to the non-homogeneous equation. So the theorem says the general solution of the non-homogeneous equation, and here we have the second order linear non-homogeneous equation, differential equation, can be written in the form y is equal to c1 y1 of t plus c2 y2 of t plus capital Y of t, where y1 and y2 form a fundamental set of solutions to the corresponding homogeneous equation, and capital Y is any solution of the non-homogeneous equation. And just to reassure you, we have learned how to find the lowercase y1 and lowercase y2, the fundamental set of solutions to the homogeneous equation. We have not yet found capital Y, but that's what the method of undetermined coefficients will help us with. And the proof of this theorem comes directly because of this relationship, the previous theorem, between solutions of homogeneous and non-homogeneous differential equations. In particular, we had that y1 of t minus y2 of t is equal to a linear combination of the fundamental set of solutions, which means we can solve for y1, and that's going to be a linear combination of the fundamental set plus a particular solution. That is a particular solution of the non-homogeneous differential equation. As I have mentioned, we haven't yet learned how to find this particular solution of the non-homogeneous differential equation, but that's exactly where the method of undetermined coefficients come in. The main advantage of the method of undetermined coefficients is that it's a very straightforward method to use. The main disadvantage is it's limited. It's usually only for problems in which, one, the homogeneous equation has constant coefficients, so this is something you want to realize, that it's for constant coefficients, and second, that the non-homogeneous terms, that is the g of t, is restricted to a relatively small class of functions, that is polynomials, exponential functions, sines, and cosines. And these two restrictions are captured in my summary of the method of undetermined coefficients, One, here I show that we're talking about functions with constant coefficients, and then two, we're talking about where g of t is an exponential function or a sine, cosine, or polynomial, or sum or products of such functions. And then we have the polynomial, the exponential, the sine or cosine. I would really like to be able to have this whole method here, just as it is on this slide, on the top of each slide as I go through examples. However, if I did that, it would be so long, it would hardly give me any room to work examples. So what I have done is I've put the first step, the second step, and the third step. But for the second step, I only put the portion that we're working with. So if we have a polynomial, I only put this part here. If we're working with an exponential function for g of t, I only put this part here. And if we work with sine or cosine, I only put this part here. So here I have kind of a summary of the method of undetermined coefficients, and because g of t is equal to an exponent, I only put the relevant portions about the exponent. So our example is to find a particular solution of y double prime minus 3y prime minus 4y equals 3e to the 2t. And the idea is we want to find a particular solution, which we will call capital Y, and capital Y is, by the way, is called a particular solution, such that capital Y double prime minus 3y prime minus 4y is equal to 3e to the 2t. And as we saw when we were looking at nonlinear differential equations, since the exponential function reproduces itself when differentiated, a good candidate to look at for y of t would be some multiple of e to the 2t. So we're going to assume that y of t is equal to a constant, times e to the 2t. And in our summary over here, we have if g of t is an exponential function, then assume y of t is proportional to the same exponential function. In other words, if g of t is equal to c e to the at, we're going to assume capital Y, our particular function, is equal to capital A, where A is a constant, e to the at. What is left is to find capital A. We can take the first derivative of y, and that will give us 2a e to the 2t, and the second derivative will give us 4a e to the 2t, and now we're going to plug our y prime, and y double prime into our differential equation. That is, the y double prime minus 3y minus 4y is equal to 3e to the 2t. So each of these, y prime, and y double prime, have e to the at, so I'm going to e to the 2t, so I'm going to factor that out. And what I'm left with is for y double prime, I have 4a. For y prime, but I have to multiply by minus 3, so minus 3y prime, that will give me minus 6a, and then minus 4y, I'll have the minus 4a. When I add the 4a minus 6a and minus 4a, well, these cancel out. So I get minus 6a multiplied by e to the 2t. And for my differential equation, I have that this must equal to 3e to the 2t, which means a is equal to 1/2. So now I know my particular solution is minus 1/2 e to the 2t. And here you can kind of see why that this method works best for the sines, cosines, polynomials, and exponents. Well, one, you know that exponents is closely related to sines and cosines when we looked at Euler's formula in one of our previous videos. And also, just you know that we chose e to the t, or e to the at, because when you take the derivative, you still get back e to the at. And that's sort of true as sine and cosine. When you take the derivatives, you keep switching back and forth between sine and cosines. And polynomials, you take the derivative of a polynomial and you still get a polynomial. So these are kind of the ideas of why these functions work well with the method of undetermined coefficients. In this next example, we have the same left-hand side of the equation, y double prime minus 3y prime minus 4y. But now our g of t is equal to 2 sine of t. Over here in my summary of method of undetermined coefficients, I have the line that talks about sine, g of t being sine or cosine. But before we look at what the solution is, we're going to do this problem and see how it's derived. So we're going to do something very similar to what we did for the exponent. And we're going to assume that y is equal to a sine of t. Then we can calculate y prime, which will be a cosine of t, and y double prime will be minus a sine of t. Now we look at our differential equation that says that y double prime minus 3y prime minus 4y equals 2 sine of t, and we plug in our proposed y here. And that will give me y double prime, which is minus a sine of t, minus 3y prime, which is minus 3a cosine of t, minus 4y, which is minus 4a sine of t. And according to our differential equation, that's going to equal to 2 sine of t. Now when I solve this equation, I can combine my sine of t, so I have a 2 sine of t. I move this over, and I move this over, and I get another 5a sine of t. And then when I move this over, I get plus 3a cosine of t, and that should equal to 0. So the value of a should work for anything I plug in for t. So let's consider t equals 0. At t equals 0, this goes to 0, and what I get is 3a, and this goes to 1. So what I get is 3a is equal to 1. That only leaves me a is equal to 0. But let's consider t equals pi over 2. So now this goes to 0, this goes to 1, and I have 2 plus 5a is equal to 0, which implies that a is equal to 2/5, or minus 2/5, which means there's no choice of a that will hold for all t. So something went wrong, and essentially it was our assumption when we assumed that y is equal to a sine of t. We need to try something different, and really one of the things to note is when you have this sign and you take the first derivative, you start getting cosines in there. So that's kind of what's throwing things off. So we're going to take a second try. So this assumption was not right. Now we're going to assume that y of t is a linear combination of sine of t and cosine t. That is, y of t is equal to a sine of t plus b cosine of t, and we just need to figure out what a and b are. We start by taking the first derivative, and then the second derivative, and then plugging into our equation. And what we get is y double prime, which is equal to minus a sine of t minus b cosine of t, which is here, minus 3 times y prime, which is a cosine of t minus b sine of t, which is here, and then minus 4 times y of t, which is a sine of t plus b cosine of t, and remember that is going to equal to 2 sine of t, which I have here. And also here, I gathered all my sines together and all my cosines together on the left-hand side and set it equal to 2 sine of t. So again, you can see I have two knowns, that is a and b. So I want two equations. So I'm going to set t equal to 0. This sine of t sets this to 0. This will be 0. So cosine of t is equal to 1. So what I get is my minus 5b minus 3a equals 0. To get my second equation to solve for a and b, I'm going to set t equals to pi over 2. So now this becomes 0. This becomes 2 because sine of t is 1. And this becomes 1. So what I'm left with is, what I have, 5a plus 3b is equal to 2. So now I have two equations for my two unknowns of a and b, and that will allow me to solve for a is equal to minus 5/17 and b is equal to 3/17. So my particular solution, capital Y, is equal to minus 5/17 sine of t plus 3/17 cosine of t. And just to come back up here, so I said if g of t is sine of b of t or cosine of t, then we are going to assume our particular solution, capital Y, is a linear combination of sine of bt and cosine of bt, which is exactly what we did here. And here I said g of t is equal to sine of bt, or g of t is equal to cosine of bt, which is exactly what we had here. And y of t is capital A cosine of bt plus capital B sine of bt. And here's yet another example. Again, same left-hand side, y double prime minus 3y prime minus 4y equals, and now our g of t is equal to 4t squared minus 1, a polynomial. So here in this method of undetermined coefficients, I copied the portion about polynomials. And essentially, if g of t is a polynomial of degree n, here we have a polynomial of degree 2, we're going to assume the particular solution, capital Y, is a polynomial of degree n as well. For this example, we are going to assume the particular solution, capital Y of t, is a naught t squared plus a1t plus a2. So we have three constants. we can take the derivative, y prime, then will equal to 2a naught plus t plus a1, and y double prime is equal to 2a naught. And then we plug that into our differential equation. So we have y double prime, which is 2a naught, minus 3y prime, which is 2a naught t plus a1, minus 4 times y prime, or sorry, 4 times y, which is a naught t squared plus a1 t plus a2. And then according to our differential equation, that's equal to 4t squared minus 1. Our terms that have no t or t squared in it, just the constant terms. I get 2a naught here. I have my minus 3a1 here. And over here I have my minus 4a2. And that will equal to my negative 1. Now grouping my t coefficients. So where do I have t? Factors of t. I have a minus 6a naught t. And then over here I have a minus 4a1 t. Since there's no t in g of t, no t term in g of t, that's equal to 0. Now looking at my t squared terms, I have none here, none here. I have minus 4a naught t squared is equal to 4. Solving these 3 equations for 3 unknowns, a1, a2, and a0, I get that a1 is equal to positive 3/2, a2 is equal to negative 11/8, and somewhere I solved for a naught. A naught was equal to negative 1. And actually in this problem, like solving these 3 equations is the thing that took me the most time because I kept having algebraic errors. And it wasn't even the algebra, it was the arithmetic of adding these fractions, so I'm a little bitter that I spent so much time having to get that. And that gives me y of t is equal to my minus t squared, my 3/2 t, and my minus 1/8. And I just kind of checked the arithmetic to make sure that this y of t was correct, but unfortunately I did my arithmetic correctly, and I even added my fractions correctly, and I do get that this capital Y of t, this particular solution, does satisfy the differential equation. And I do want to remind you that here we have found the particular solution, and the general solution of the non-homogeneous equation is equal to the a fundamental set of the homogeneous equation plus the general solution of the non-homogeneous equation. So in this, what we've been solving for is just this capital Y of t. So we haven't found the general solution. Not that it would be hard, but just that we haven't done that. And for our next example, again, we have the same left-hand side. There's a reason for that, and we're going to come to it soon. But the same left-hand side, y double prime minus 3y prime minus 4y. And now our g of t function is equal to minus 8 e to the t cosine of 2t. And so what you see here is you have an exponent times a cosine function. And what we're going to use is this portion, bullet point number 1, in finding capital Y of t, the particular solution, which is if g of t is a sum of 2 functions, one might be an e of t, one might be a cosine of t, then we solve each individual one, and then we add the results. We'll do an example of this in particular soon. But also, if g of t is a product of any 2 or 3 of all these types of functions, that is exponent, cosine, sine, or polynomial, then we use the same approach. We assume the solution is a product. So here we have an e of t and a cosine of 2 of t. We are going to assume our solution, our particular solution, is a product of e to the t and cosine. And that's exactly what we're going to do here. We're going to assume y of t is a product of e of t and cosine of 2t plus sine of 2t. So y of t is equal to a e to the t cosine of 2t plus b e to the t sine of 2t. Also up here, there is another point for g of t. If it's a product of a polynomial, an exponent, and a sine, or a product of a polynomial, an exponent, and a cosine, then this is the form, the general form, which we have here. The t of s is something we'll talk about later, but we have the e to the at cosine of 2t times In this case, it's not a polynomial, but just a single constant because we don't have another polynomial in front of here. And we have e to the at sine of bt. And again, there's no polynomial, but it's just a constant multiple. And as we've done, once we have our y, we can calculate our y prime and our y double prime and then plug in to our differential equation. So here I have my y double prime, which is over here, my minus 3y prime, which is here, and my minus 4y. And now I can group my e to the t cosine t terms and my e to the t sine 2t terms. So from grouping e to the t cosine 2t for my y double prime, I have my minus 3a plus 4b. And then from my y prime, I get my 3 times a plus 2b. And from my y, I get my 4 times, and I'm looking for cosine, a term. And then grouping for sine of t similarly, for my y prime, I have my minus 4a minus 3b term. From y prime, I have my minus 3, what do I have? Minus 2a plus b. And for my y term, I have my minus 4b. From here, I have minus 3a, minus 4a, minus 10a. I have 4b minus 6b, so I get minus 2b. And this here should be equal to minus 8, because that's the coefficient in front of my e to the t cosine of 2t. Similarly, looking at my sine, doing the arithmetic, I get 2a minus 10b. And since there's no sine term here in g of t, that should be equal to 0. That allows me to solve so that a is equal to 10 over 13 and b is equal to 2 over 13. And my general solution is 10 over 13 e to the t cosine of 2t plus 2/13 e to the t sine of 2t. And now our next example, where you get to see why I kept saying same left-hand side, y double prime minus 3y prime minus 4y. Now our right-hand side, our g of t, is equal to 3e to the 2t plus 2 sine of t minus 8e to the t cosine of 2t. So you might recognize this as the example we just worked, and these are the other two examples we worked. And this is where we are going to use this part of our method of undetermined coefficients. If g of t is equal to the sum of simpler functions g1 and g2, in this case we have 3. We have g1 is equal to 3e to the 2t plus, so again it's the sum, plus another g of t, 2 is equal to 2 sine of t, plus, and our last g of 3 is minus 8e to the t cosine of 2t. We can then solve these equations one at a time for g1, then for g2 and g3, which is exactly what we did in the previous 3 examples. And then we can add the results. So let's do that for this problem here. Again, the idea is we take this differential equation and we break it up into 3 parts, where this is our first equation, g1, 3e to the 2t. This is our second equation, 2 sine t. And our last equation, g3, is equal to minus 8e to the t cosine of 2t. If we look back at our last 3 examples, we saw that the solution for our first g1, 3e to the 2t, is equal to minus 1/2 e to the 2t. Our solution when g2 is equal to 2 sine of t was equal to minus 5/17 sine of t plus 3/17 cosine of t. And our last solution to this g3, which is minus 8e to the t cosine of 2t, was 10/13 e to the t cosine of 2t plus 2/13 e to the t sine of 2t, which means for this non-homogeneous differential equation, our particular solution is equal to y1, which is 1/2 e to the 2t, plus y2, which is minus 5/17 sine of t plus 3/17 cosine of t, plus y3, which is 10/13 e to the t cosine 2t plus 2/13 e to the t sine of 2t. So this looks like a very long example to do, but if you break it up into pieces, each part is quite manageable. This is our last example where we explain this little asterisk here that goes with this formula here. And there's a danger. So we want to find a particular solution, again, same left-hand side, y double prime minus 3y prime minus 4y is equal to 2e to the minus t. We assume a solution because it's an exponential that we have a constant multiplier times the exponential. we take the first derivative, the second derivative, we plug into the differential equation, factoring out the a to the e minus t. We have y double prime, which is 1 times a to the e minus t. We have minus 3y prime, which will give us a plus 3 times our a to the e minus t, minus 4y prime, which gives us minus 4 times a e to the minus t, which gives us 1 plus 3 plus 4 is 0, and by our differential equation is equal to 2e to the minus t. So why is this a problem? Well, to see that, we'll consider the homogeneous equation y double prime minus 3y prime minus 4y equals 0. Looking at the characteristic equation, r squared minus 3r minus 4, we get that r is equal to 4 and r is equal to negative 1. In other words, y1 is equal to e to the t to the minus t, and y2 is equal to the e to the 4t. That brings us to the problem that here, what we have proposed as our particular solution is actually a solution to the homogeneous equation. So when we try to get our general equation, we don't have two independent solutions here. To figure out how to solve this problem now, this differential equation, y double prime minus 3y prime minus 4y equals 2e to the t, we're going to step back and consider a related but similar problem, and then try to figure out how that's going to help us solve this current equation. Here's the problem we are trying to solve, and this is kind of a related problem that we're going to study. So it's y prime plus y equals 2e to the minus t. In particular, we chose a linear equation to look at. Since it's linear and also first order, we solve this using an integrating factor mu of t is equal to e to the t. We multiply our entire equation by e to the t to get y prime e to the t plus y e to the t. This times this just leaves us with 2. And remember, our integrating factor is chosen so that once we take the derivative of both sides, the derivative of the left-hand side is just equal to y times our integrating factor. And then on the right-hand side, taking the derivative with respect to t, we get 2t plus c. So in other words, y, dividing both sides of the equation by e to the t, y is equal to 2t e to the minus t plus c e to the minus t. And here it is. This is what we're going to use. This is the general solution to the homogeneous equation, y prime equals y plus 0. Whereas this is the solution to the non-homogeneous equation, where we have this 2e to the minus t. So what this suggests to us is that once we have a general solution to the homogeneous equation, we can try to multiply our solution to the homogeneous equation by t and see if that will give us a solution to our non-homogeneous equation. And that is exactly what this is saying here. We potentially need to multiply our solution by t, and t could be either t to the 0 if there's no problem, t to the 1, and that's what we're going to try here, or if we still need to, we might have to multiply by t squared, but we won't have to multiply by anything larger. So here is what we attempted before, but I crossed it out. But just to remind you, our initial attempt at the particular solution was just a scalar multiple of our exponent. But now we're going to assume y of t is equal to a times t times e to the minus t. We can calculate y prime, y double prime, plug it into our differential equation. So I did some algebra, which I didn't show all of it here, but I did group my e to the minus t terms and my t e to the minus 2t terms. And all of this by the differential equation is equal to 2 e to the minus t. So what this tells me is, since I have no t e to the minus t terms over here on the right-hand side, that must mean my a plus 3a minus 4a equals 0. And then here, my e to the minus t terms, that is minus 2 minus 3a, must equal to 2, the coefficient in front of my e to the minus t. So this gives me that a is equal to minus 2/5, and my particular solution is now equal to minus 2/5 t e to the minus t. And again, we multiplied the solution by t in order to ensure that y, our particular solution, is not a duplicate of the homogeneous equation, not a duplicate of the solution of the homogeneous equation. Time to review. What have we looked at? We looked at the first theorem that says there's a relation between the solution of the homogeneous equation and the non-homogeneous differential equation. So if y1 and y2 are solutions of the non-homogeneous equation, that looks like this. It's second order because of the second derivative, linear, non-homogeneous because there's a g of t that's not equal to 0. And what else is there? Possibly non-constant coefficients. So y1 and y2 are solutions of this equation. Then their difference, y1 minus y2, is a solution of the corresponding homogeneous differential equation. In other words, this exact same equation, except instead of equal to g of t is equal to 0. If, in addition, y1 and y2 form a fundamental set of solutions to the homogeneous equation, then y1, our particular solution, capital Y1 minus capital Y2, is a linear combination of our fundamental set of solutions. We had our second theorem that gave us the general solution of the non-homogeneous equation, and the form of this general solution will be a linear combination of the fundamental set of solutions to the homogeneous equations plus a particular solution, capital Y of t, of the non-homogeneous equation. And the theorem says the general solution of the non-homogeneous equation, given here, it's a second order, linear, non-homogeneous, with possibly non-constant coefficient equations. So the general solution of this can be written in the form y equals c1 little y1 of t plus c2 little y2 of t plus capital Y of t, where y1 and y2 form a fundamental set of the corresponding homogeneous equation, and capital Y is any solution of the non-homogeneous equation. And as I mentioned in previous video, we found out how to find this fundamental set of homogeneous equations. So what we needed to do in this video was figure out how to find the solution of a non-homogeneous equation. And that's where the method of undetermined coefficients come in. And the method of undetermined coefficients, it's a good method in that it's fairly straightforward. And actually it looks long, but it's really not, because part 2 has many cases, but they actually break down very similarly. So it's easy to understand, very straightforward. The problem with it is that g of t, this thing here that makes it non-homogeneous, needs to be an exponential function, a sine function, a cosine function, or a polynomial, or sum of or products of these type of functions. So it's limited. And what we would do for our method of undeterminate coefficients is find a general solution of the corresponding homogeneous solution, and those are called the complementary solution. Then we would find capital Y of t, a solution of the non-homogeneous equation, and this capital Y of t is called the particular solution. First bullet is sort of a note that if g of t can be broken up into simpler functions, the sum of two simpler functions, then we can solve the equation using just the simpler functions and then adding the results. Also, if we have a product, then we can just assume sort of the same principle that our solution is going to be a product of these type of functions, and we'll do an example of that, or we did an example of that. So these are the three cases. If g of t is a polynomial of degree n, then we assume our solution, our particular solution, is a polynomial of degree n. So if g of t is equal to polynomial of degree n, y of t is also a polynomial of degree n. If g of t is an exponential function, then y of t is going to be proportional to the same exponential function. So if g of t is equal to c e to the at, then y of t is equal to a e to the at. If g of t is sine of bt or cosine of bt, then we're going to assume y of t is a linear combination of sine of bt and cosine of bt. So g of t is equal to sine of bt, or g of t is equal to cosine of bt, then y of t is equal to a cosine of bt plus b sine of bt. And then we had this general form here, which goes with this comment about a product of any two or three of this type. So if we have a product, if g of t is a product of a polynomial, an exponent, and a sine, or if g of t is a product of a polynomial, an exponent, and then a cosine, then our y of t is going to be of the form of a exponent times a cosine times a polynomial plus an exponent times a sine plus a polynomial. And we also had this ts over here, and that was our last example. So if y is a duplicate of the solution of the homogeneous equation, we multiply our y of t by another factor of t. And possibly we'll need to factor by t squared, but never more than t squared. So that's what this note was about. And then finally, we find the sum of the functions y, our general solution, is equal to linear combination of the fundamental set plus our particular solution. And just a note, in this video, we focused on finding the particular solution, and often we didn't find the general solution because we didn't do these extra steps here on part 3. And that's it for this video. Thank you for watching.